Welcome, I'm Carl Tate. The topic here is global plate tectonics, plate motions. We'll start with an example showing two different units of speed. We'll need some practice in the labs and work in converting between units. And we'll start with how many kilometers per million years correspond to 1 millimeter per year. So we start with 1 millimeter per year, and we want to convert units by multiplying by 1 again and again. And by 1, I mean the thing on the top, 1 meter, is equivalent to the thing on the bottom, 1,000 millimeters. So this means multiplying by 1. What we choose is a way to get rid of the units. If we want to get rid of millimeters, we're going to put it on the bottom until we find the units we want on top, which is kilometers. So we multiply here, we get meters on top, we put meters on bottom, multiply by 1 here. And now we want to convert from the years to million years. So we put 1 million years on top. We have 1 million years on bottom. And then we start canceling units on top and bottom. Millimeters, meters, years. And we're left with the units kilometers on top, million years on bottom. That's what we want. The question is, what number goes out in front of that? And for that, we need to look at the numbers on the left-hand side. There it turns out we have 6 zeros here in the 1 million. We have 3 zeros here in 1,000, 3 zeros here. So these numbers cancel out. And so the number out front is just the number you start with. If we started with 5 millimeters per year, we'd have 5 kilometers per million years. We started with 1 millimeter per year, so we have 1 kilometer per million years. So this is kind of a useful thing to remember, because you might imagine a geologist talking about plate motions will use units of kilometers per million years. She might be measuring, say, the age of rock samples collected from the seafloor that may differ by millions of years, and they may be kilometers apart, trying to say something about plate motion, for example. Someone measuring plate motions with a GPS will use units of millimeters per year, say, taking a measurement every minute or every second or once a month. You'll take all these measurements of the location of some point or marker in Alaska and use that to measure how many millimeters over the year that it moved. And that would give you a rate of millimeters per year for that motion. The choice of units indicates the time scale you're most interested in, or perhaps the time scale that the data were used to measure. As an aside, here's an example of converting from millimeters to inches just to get some practice. So say the Pacific plate moves at about 75 millimeters per year. How many inches is 75 millimeters? Well, first of all, take a guess. Hold out your fingers. There's a pretty good clue here at the left, but 3 inches turns out to be 75 millimeters. And we can see that by converting 75 millimeters by multiplying by 1, that's centimeters per 10 millimeters, multiplying by 1 inch per 2.54 centimeters, and we get 2.95 inches, basically 3 inches. So here we show at the left, there's 3 inches, and there would be 75 markings along this in millimeters on the ruler. So it doesn't seem like much. We're talking about how far the Pacific plate moves in a year. So now let's just see kind of an example of this unit conversion. Say we want to go from millimeters per year to miles per hour. They're just units of length over time. They're both speed. So here we start with the speed of the Pacific plate, 75 millimeters per year, and we multiply in a manner that will convert our units of length, which are millimeters. We're going to convert that to miles, and we're going to convert years to hours. So here's the sequence of multiplying by 1 needed to make this silly conversion, but good practice. Besides, we all know miles per hour. You then can collect the numbers. So you got a 75 on top, and there's a 10, 2.54, 12, 5280, 365, 12. All those numbers get collected on the left. These are all products, so we can separate the units from the numbers and multiply top and bottom. We have the units of millimeters, centimeters, inches. Here are all the units on the top. And then we can cancel, as intended. We should be canceling all these units down until we have miles per hour. And then on the left, we have the number, a very large number on the bottom, 75 on the top. It turns out it's 0.0000466 miles per hour. You are not going to get a speeding ticket. The Pacific Plate will not be getting a speeding ticket anytime. In miles per hour, yeah, that sure seems slow. And even inches per year, 3 inches per year, that seems slow. Yet when attached to a massive tectonic plate, it's enough to form the spectacular features on Earth: mountains, volcanoes, islands, even earthquakes. So this sort of slow, seemingly slow rate gives us the magnificence of really the natural world around us. The physical features on the planet arise from this pretty slow, innocuous sounding rate. Okay, describing the motion of plates on Earth. The Earth is described in terms of this set of plates, and we're going to extract the Pacific Plate as an example. The plate is described by its boundary, shown here. Its motion is described by what is known as an Euler Pole, which is an imaginary axis passing through the center of the Earth. And this is the axis, the back end and the front end. To imagine the Euler Pole in this symbology, imagine shooting an arrow. Pull out an imaginary arrow, aim it straight down, shoot it downward in the Hudson Bay. It would come out the other side of the planet. After going through the center, it would come out somewhere out here, south of Australia. The feathers of the bottom of the arrow is the X symbol, like you're looking at the back of an arrow. And the tip of the arrow, like the tip of a cone, looks like the dot with a circle around it. So that's the symbol for the tip of the arrow and the feathers. And it matters which direction it's going, as it turns out. So here's our Euler Pole for the Pacific Plate motion on Earth. Now we look at the velocity field, or the speed of things on the surface associated with this Euler Pole. And things look more complicated than they really are. This is just the motion of a sphere spinning on an axis. The color corresponds to the size of these arrows, the magnitude, and they range from 0 millimeters per year to something like 85 or so millimeters per year. So it's just the motion of a sphere spinning on an axis, which would be the Euler Pole, like spinning a basketball. And there we have spinning a basketball. You could watch that and think about spinning a basketball. And in this case, the finger is the Euler Pole and the ball would be the Earth. If we think about the speed of this ball, or the surface of the ball, the speed is slowest near the finger and fastest at the equator of this ball, sort of as defined by this Euler Pole. And if we look at the colors here on the right, the purple speeds down near 0 are near the Euler Poles, and the fastest speeds are shown in orange, the kind of equator of this Euler Pole as defined. This motion describes only the Pacific Plate, and this is the Pacific Plate here. So first we show just on the sphere, we got the spinning basketball idea, but actually that only describes one portion. And we can see if we add the coastlines just to make sure we know what we're looking at. This is the large plate that occupies much of the Pacific Ocean. And we can now cut it out. So we extract that portion and say this part of the Earth is how it moves. So here's the motion. The surface speed is fastest near the center, the orange, at about 85 millimeters per year, and slowest in the north and south at about, say in the green here, low green's 55 millimeters per year. Although the surface speed differs, it moves as a rigid body with constant angular velocity. So like the basketball, the surface speed changes, but it's moving like a rigid body. And here we have, without any of the color, the vectors show the direction and the length shows the speed. Each plate has its own Euler pole to describe its motion. So there should be 56 dots on this map. These are the Euler poles, the positive direction, the tip of the arrowhead. We see the Pacific shown here, where it gets its back end as well, shown in red, and each of the other plates has its own Euler pole to describe its motion. So let's showcase one other, North America. It looks kind of funny in this display since it contains the top of the Earth, including the North Pole. So just the way the map is, things look a little funny, but that's okay. We need to understand and reinforce how this goes. So the North America Euler Pole is an arrow shot straight downward near Japan here. It passes through the center of the Earth and comes out in the South Atlantic Ocean. Here's the North America plate, and there's its Euler pole. Again, spinning basketball. We can think of the spinning basketball. This is the Euler pole, and this shows the motion of the entire Earth if it were moving as North America moves. The analogy here is we need to slow down this movie a little bit because the ball is moving slower. We've got blue colors instead of green, so North America is not moving very fast. This motion describes only the North America plate, only the portion inside this boundary. We can see the coastlines here. So we cut out the portion inside the boundary. And that's our North America plate motion. It moves slowly relative to the hot spots. This blue here is about 20 millimeters per year. And the lower 48, for example, this portion, if you look in here, you'll see these arrows are moving approximately in the southwest direction. And we'll come back to that in a bit. Again, our picture of North America plate motion. So we have the Pacific plate. We did the North America plate. And those are used to fill in the pieces of the puzzle, where we kind of created the puzzle pieces as defining the plate boundaries, but now we need to assign their important speeds and velocities. So we did 2 of these, and so you do this for these other 54 plates in this model, and we fill in all the pieces. Each plate defined by its boundary and defined by its Euler pole, and that gives us the motion. Here they are, Pacific, North America, and 54 plates. Takeaway topics. Plates move as rigid bodies on the surface of the Earth. Plate speeds range from 10 millimeters per year to about 100 millimeters per year. A plate's motion is defined by its Euler pole. Not really a takeaway topic, but just something to keep in mind. These plate motion models, such as a set of Euler poles, provide a simplified view of the motion of plates on the Earth's surface. These models are based on observations such as GPS measurements of motion. Your smartphone knows your location by GPS, as well as geological information of seafloor spreading from rocks on the seafloor.